Hi, my name is Isabel Gonzalez, and in this video I'll introduce the fundamentals of X-ray diffraction, what it is, when to apply it, and how to analyze it. I'll also share real data from my research on AgTiO2 HNT nanocomposites. X-ray diffraction, or XRD, is a non-destructive technique used to determine the crystal structure and crystallite size of a material. It relies on Bragg's law, which describes how X-rays reflect on parallel atomic planes in a crystal. When the conditions for constructive interference are met, we see a diffraction peak at the specific angle theta. This is expressed in the equation, where lambda is the wavelength of the incident X-ray beam, typically copper K alpha, or 1.5046 angstroms, and d is the interplanar spacing. The positions of these peaks help identify what phase is present, while their width can help us estimate particle size. Now, how does this complex instrument work? This is what the inside of a typical powder X-ray diffractometer looks like. The main components are the source, which generates the radiation, the primary optics, which focus and align the beam, the sample holder, which contain powdered or film-coated material, secondary optics, which help collect the diffracted rays, and finally the detector, which rotates around the sample and measures the intensity of diffracted X-rays at various 2 theta angles. The final output is a graph of intensity versus 2 theta, which we interpret as the XRD pattern. Next, we'll examine how to interpret the graph. Each peak position on an XRD graph corresponds to a specific interplanar distance, or d-spacing, in the crystal lattice. The intensity of a peak reflects how frequently that atomic arrangement occurs and whether there is preferred orientation. Peak width, on the other hand, can tell us about crystallite size. Broader peaks typically indicate smaller crystals. We estimate this using the Scherer equation, where d is the average crystallite size, beta is the full width at half maximum, and theta is the Bragg angle. In this example, comparing anatase and rutile TiO2, anatase has a peak at 25.3 degrees, while rutile peaks at 27.4 degrees. A broader anatase peak with an FWHM of 0.2 degrees corresponds to a particular size of approximately 15 to 20 nanometers. To further explain this, let's take a look at the XRD of our AgTiO2 HNTs, actual data from our project. The black curve represents pure halocite nanotubes, which show characteristic sharp peaks at 12.2, 20.1, 24.8, and 35.4 degrees, confirming a well-ordered natural crystalline structure. In the red spectrum, which corresponds to the AgTiO2 HNTs, we see new peaks emerge at 25.4, 44.5, and 48 degrees. These indicate the successful deposition of anatase phase TiO2 and metallic silver nanoparticles onto the HNT surface. Importantly, the original HNT peaks at 12 degrees and 20 degrees are still present. This confirms that the tubular framework of the clay remained intact during composite formation. In the blue spectrum, we analyze the same composite after functionalization with a binary surfactant less than 80. The peaks correspond to this surfactant at 25.3, 38.2, and 44.6 degrees. And so that suggests a smaller crystallite size and increased surface disorder. This is consistent with better nanoparticle dispersion and high photocatalytic surface area. Using the Scherer equation, we could estimate the size of these nanoparticles, and we estimate that they fall in the 20 to 30 nanometer range, which supports nanoscale function. While XRD is essential for determining crystal structure, phase composition, and crystallite size, it may not be the right technique for you, or it may be only one part of your complete material characterization toolkit. For instance, techniques like FTIR are used to identify chemical bonds and surface functional groups, which is crucial for confirming surface modifications or molecular interactions. SEM provides direct visualization of surface morphology, allowing researchers to examine particle shape, dispersion, and structural uniformity at the micro and nano scale. TGA evaluates thermal stability and compositional changes, making it useful for quantifying organic content, surfactant loading, or thermal decomposition behavior. Each of these methods offers unique insight, and together they could provide a comprehensive understanding of material structure, chemistry, and function. In summary, X-ray diffraction is a technique that is essential in material science, chemistry, environmental remediation, and more. Where confirming the formation, structure, and stability of material may be key to designing effective solutions. For our AgTiO2 HNTs, we found that they contain anatase TiO2, retain HNT structure, and have well-dispersed silver in the nanocrystalline range. These are my references, and thank you for watching.